Uh, Now, which type of cables are used by the standard Ethernet? So standard Ethernet basically uses coaxial cable called as a bus topology or a set of twisted pair cable. Twisted pair cable. It is called TPC, right? And sometimes we have UTP also, untwisted pair. This thing, and then with a hub in star topology. So we'll see that arrangement, how exactly it is done. And transmission, you should keep in mind in standard Ethernet is always a broadcast. No matter if the address is unicast, multicast, or broadcast, but it is in standard Ethernet, every frame is treated to be, going to every source that is connected to the network. Now in bus topology, when a station, bus topology is something like this. Bus topology is something like this. Like you have a central bus here, you have, sorry. So you have a central bus here, right? This is the central bus. And this is the station connected to it. So this is the sending host and this is the, say, receiving host. And several systems will be connected here. Several systems will be connected here. So this is the bus topology. The single bus will be there to which different hosts are connected. So suppose this is the sending host A, and this is receiving host B. So this particular station is B, and this particular station is, say, A. You got the idea? So now, whenever I'm saying that a frame is sending, A is sending a frame, which has to be received by this station, this station, this station, every station except A, every other station that is connected to the network that is connected, so they will be receiving. Now B, whenever it receives the frame, it sees its MAC address. So what it will be doing is it gets the frame and it processes it. Now, if it is through what I meant to say, star topology, in which star topology means it is something different kind of arrangement. So we have seen the star topology where there will be a central hub. You got the idea, to which the stations will be connected like this. So this is the star topology. So the stations are connected in a star fashion. Stations are connected in star fashion. So I can show like this, right? I can show like this. So this is the central hub. This is the central hub that is there. So whenever any station that wants to send data, suppose this is A, and this is the station B. So station A and this is station B. Station A wants to send a frame to station B. So it has to send the frame to hub first. This is the hub, central hub. So to this hub, it will send the data. So this is my hub. So to A will send the data to hub, and the hub in turn will send that to what I meant to say, this particular station B, right? So and it also sends the data to all other stations also. It does not check the destination address of the frame. Simply it will regenerate the bits zeros and ones. It will send it to all the stations except uh, from the station where it is coming from. If the frame is coming from A, the frame will not be A is the frame is coming from A. Hub will send the frame to this station, this station, this station, this station, and this station, except station A. This is what has to be understood, right? So basically, you have seen that hub is actually flooding the entire network with the frames. So this is the bus topology, what is a coaxial cable, and at the end you have taps. That means the frame will pass here also. I meant to say, suppose here G is sending a frame for B, meant for B. So the frame will be going in this direction, frame will be going in this direction. That means the frame sent by G is received by H, as well as this tap also. It is received by F, E, D, C, B, and A, and this tap. Tap will simply take what? This will take the frame and it will destroy it. It will destroy it. After that, it will not release the frame to go back into, so frame will not rebound into the network. So it will be destroyed here. But when the frame from G is received by A, it sees whether that frame is containing its MAC address. If it is not, suppose G wanted to communicate with D, so the frame from G has gone to A, B, C, D, E, F, and H also. But since the frame from G is meant for D, so D will find destination address as its MAC address. So D will do what? It will decapsulate the frame and send it for processing at upper layer. Whereas all these other stations will drop the packets, because this particular frame which has been sent by station G is not meant for them. And now here we have this star topology, which is nothing but there is a hub to which various station A, B, C, D, E, F, G are connected, G, H are connected. So suppose station E wants to send data to station D. So in this case, it will send data frame to the hub. Hub will not check the destination address. What it will do is it will simply regenerate all the bits, like zeros will be restored to zeros and ones will be restored if the signal strength has come down. Since as I told you in the very first module, that these bits that are being sent are converted into voltages, electrical signals. So voltages. So if it is 5 volts has become 3 volts, so it will be made to be 5 volt. And 11 volts has become, say 11 volts is representing 1. So it has become, say 8 volts. So that will be again, what I meant to say, regenerated to 11 volts. And then frames will be sent to each of the host except the sending host. That is E has sent. So except this, the frames will go to all other, what I am say this thing. So there is a hub, there is a host. This is a cable, what I meant to say, and cable end that is called as a tap where the frame is destroyed, and this is coaxial cable, and this is twisted pair cable. So this is the whole arrangement. So if it is unicast transmission, all station will receive. So whether it is unicast, multicast, or broadcast, it is actually is a broadcast in a Ethernet. So the standard Ethernet, it is broadcast only always. So unicast will do what? The station for which it is meant, if it sees that this is my MAC address present in this is my MAC address, so it will take that frame and for processing, it will send it to upper layer, and remaining will be of the, what I meant to say, this thing will be discarding it. Remaining host will discard it. Multicast. So all the stations that are part of multicast group will have their MAC address in it, multicast address in it. So if that station is a part of that multicast group, it will decapsulate the frame, and it will send it for further processing to upper layer, and otherwise it will discard it. And broadcast, anyway, the frame has to be decapsulated by all the stations, and they have to be processed. Next is, since what I meant to say, Ethernet protocol is nothing but broadcast network only. It's a kind of a broadcast network, right? So standard Ethernet has chosen CSMA CD with one persistent method. So I had, recently taught you in module, what I meant to say, uh, mm, 4, where I had taught you the CSMA CD method. In that, one persistent method is always the sending host keeps on sensing the medium. So this is the medium. It keeps on sensing the medium at what I meant to say, regular interval of times. At regular interval of times, you got the idea whether there is a presence of electrical signal here. That is, electrical signal means whether some other station is transmitting the frame. So since it is continuously checking whether the frame is idle or busy, so here, since the voltage is present, you got the idea. And the moment it is coming here, it is finding that there is no voltage. So the moment it senses here and finds that there is no voltage, it will release its sending host will release its frame. You got the idea. So this was called one persistent method. So this is the scenario. This is the scenario which we had seen earlier. So here in figure 13.A, this station A wants to send a frame to station D, and it uses one persistent method for doing so. It uses one a persistent method for doing so. So here, let us see, station A will always measure level of energy on the medium. So for a short period of time, say 100 milliseconds. So every 100 millisecond, as I was showing through arrows, that every 100 milliseconds duration, the medium will check the, sending host will check the medium for the presence of, voltage, for the presence of voltage or for the presence of signal, electromagnetic signal. If energy, that is the electrical signal is there, it will not send, but the moment it sees that, if the medium is idle, that means no signal is there on the medium, it starts sending its frame. That's one persistent method, right? So this is there, so how does it know whether the channel is idle or this thing? So here energy level, that is electrical energy that is passing through medium, if it is not zero, indicates that the channel is busy. If electrical energy present in the channel is zero, indicates that it is free. It is what I meant to say, it is free. If it is zero, it is free, that is idle, and it can send this, right? So station A will continuously monitor the medium, right? And if it finds that the medium is busy, by finding the electrical signal, presence of electrical signal on the medium, another 100 microsecond it will wait. Then after 100 microsecond, again it will check the medium. If there is a electrical signal, that is the energy, electrical energy is present in the medium, it will again wait for another 100 microseconds. So this process is called one persistent method, right? And the moment it releases a frame into the medium, by finding that medium is idle, but before sending, it has to keep a copy of the frame, that and the moment, as I have informed you earlier, the moment a packet is sent, a frame is sent on the transmitted onto the medium, and a copy is kept, it has to start its timer to receive acknowledgement from the destination, if it is connection oriented, what I am saying, connection. So if acknowledgement doesn't come within the timer's timeout time, again it has to send the packet back, right? So this is what happens. So basically, this is the efficiency of this is how the efficiency of Ethernet protocol is measured, which is taken as 1 upon in bracket 1 plus 6.4a, where a is represented as number of frames that will fit the medium. You got the idea? It is calculated as follows. So a is defined by the formula propagation delay by transmission delay. Propagation delay by transmission delay. So that a value, if you put, I will be getting the efficiency. So there is a special case, assuming that if a is equal to 0, if a is equal to 0, indicates that efficiency is 1, means 100%. The larger the value of a, smaller the efficiency, and the smaller the value of a, it is the highest efficiency. As I have shown, if a takes the value 0, this factor becomes 0, and 1 by 1 I will be getting 100% efficiency. Now, this is what is the meaning of what I meant to say, this thing. So if the length of the medium is shorter or the frame size is longer, the efficiency increases. This is what is the, what I mean to say, this thing. Now, we have a small example in the standard Ethernet with transmission rate of 100 Mbps that is given. You got the idea, transmission rate is given, and right, and assume that the length of the medium is 2500 meters, that is 2.5 kilometers. If you convert this into kilometers by dividing it by 1000, I will be getting 2.5 kilometers. So this length of the medium can be either given in meters form or it can be given in what I meant to say, kilometers form. But here, since it is given directly in meters form, we need not make the conversion. But if it is given, this particular factor is given as 8 kilometers, this has to be converted in meters, because we have given propagation speed as 2 into 10 to the power 8 meters per second. This value is in meters, so this should always be in meters. So we have seen propagation delay is nothing but 2500. You got the idea? Length of the medium is length of the medium is this divided by the speed, which is nothing but 2 into what I meant to say, 10 to the power 8 meters per second, and this meter goes off, and I'll be getting, if you solve this, you will be getting 12.5 microsecond is the propagation delay, and the transmission delay is nothing but the frame size is given as what I meant to say, 512 bit. So the time it requires by first bit to reach the destination, then second bit, third bit, and so on. Last if 512th bit. So this time difference is calculated simply by, I got the idea, 512 divided by 10 to the power 7 is what I meant to say, 51.2 is microsecond. So A is nothing but we'll have propagation delay divided by transmission delay, which is 0.24. So 0.24, and if you put this in formula, so formula was given to us. You got the idea, as efficiency was given by the formula E is equal to 1 upon. You got the idea. This is 1 plus 6.4, right? 6.4a. So when you solve this, the value of a, I have got it as 0.24. So 1 plus 6.4 into 0.24, it will be whatever is the value, what divided by this whole value will give you 0.39. 0.39, if it gets me 0.39, is 39% is the